BETELGEUSE or Betelgeuse is a red giant star. If you put it where the Sun is, it would extend out to the orbit of Jupiter. It's enormous and very unstable. It's about to explode. These explosions are among the biggest bursts of radio energy in the entire universe, generating more energy than a billion suns. Brian Cox, a renowned physicist and science communicator, has issued a chilling warning about a mysterious phenomenon surrounding Betelgeuse, the star best known as Orion's shoulder. According to Cox, recent observations have revealed a peculiar dimming in the star's brightness, an occurrence that could signal something truly weird happening deep in the heart of this massive stellar object. But what is causing Betelgeuse's strange behavior? Could this dimming be a prelude to the star's final moments before it goes supernova, or is this just another cosmic enigma waiting to be unraveled? Stay with me as we delve deeper into the mysteries of the universe. A star in distress. When it comes to celestial bodies, size matters, and Betelgeuse is a titan among stars. This strikingly reddish star isn't your average celestial body. Its brightness wavers between +0.0 and +1.6, making it the most luminous first-magnitude star in the night sky. But here's the kicker. It's not just its luminosity that sets it apart, but also its size. The immense size of Betelgeuse is truly mind-boggling. If it were to replace our Sun at the center of the solar system, its radius would stretch far beyond the orbits of Mercury, Venus, Earth, and Mars, extending well into the asteroid belt. To put its colossal dimensions into perspective, consider this. If our Sun were reduced to the size of a ping-pong ball, Betelgeuse would be a massive structure, just like a football stadium. Think about that for a moment. Now let's talk mass. Betelgeuse's weight varies, but it's somewhere between slightly under 10 to a little over 20 times that of our Sun. As for its distance, that's been a bit tricky to pin down precisely. Estimates suggest it's somewhere between 400 to 600 light-years away from us. Quite a range, isn't it? At less than 10 million years old, Betelgeuse is a cosmic youngster, but don't let its youth fool you. It's evolved rapidly due to its hefty mass. Scientists predict it will meet its grand finale with a supernova explosion likely within the next 100,000 years. When that happens, brace yourself. Betelgeuse will shine as brightly as the half-moon for over 3 months. But here's the comforting part. Earth will remain unharmed. We'll shed more light on this soon, so relax. Now here's where things get even more intriguing. Betelgeuse isn't one to stay put. Nope, it's a runaway star that's been kicked out of its cozy birthplace in the Orion OB1 Association, the same neighborhood as Orion's belt stars. It's zooming through the interstellar medium at a mind-boggling speed of 30 kilometers per second, leaving behind a bow shock over 4 light-years wide. Back in 1920, Betelgeuse snagged another title, the first extrasolar star whose photosphere size was measured. Since then, astronomers have been busy studying its apparent size, which ranges from 0.042 to 0.056 arcseconds. But why the range? Well, blame it on Betelgeuse's quirks. It's not perfectly spherical, and its appearance changes at different wavelengths. Now let's talk about Betelgeuse's entourage. It's not alone out there. It's enveloped by a sprawling asymmetric envelope about 250 times the size of the star itself. This envelope is a result of Betelgeuse shedding mass over time, creating a captivating celestial spectacle. And guess what? Betelgeuse's apparent diameter as seen from Earth is surpassed only by a couple of other stars, our Doradus and, you guessed it, our very own Sun. But there's still so much more to uncover about this enigmatic star. Betelgeuse isn't just any old star. It's a behemoth in the cosmic arena. Classified as an M1-2 Iab red supergiant, its designation reveals a lot about its nature. The M signifies its red hue and relatively cool temperature, while Iab denotes its intermediate luminosity, placing it between a typical supergiant and a luminous one. Since 1943, Betelgeuse's spectral fingerprint has been a stable reference point for astronomers classifying other stars. Pinpointing Betelgeuse's exact luminosity is no easy feat, thanks to uncertainty surrounding its surface temperature, diameter, and distance. However, recent studies estimate its luminosity at around 126,000 times that of our Sun, assuming it's about 200 parsecs away. Temperature-wise, Betelgeuse is a bit of a chameleon, with readings ranging from 3,250 to 3,690 Kelvin, fluctuating due to atmospheric pulsations. But here's where it gets even more fascinating. Betelgeuse isn't one to rush. It's a slow rotator compared to its stellar counterparts, clocking in at a leisurely 5.45 kilometers per second. It's a snail's pace compared to speedier stars like Antares. It takes Betelgeuse a whopping 36 years to complete a single rotation, tilted at an angle of about 60 degrees to Earth. In 2004, astronomers hypothesized that despite its sluggish rotation, Betelgeuse might still boast significant magnetic activity in its expansive atmosphere. This magnetic influence could sway everything from its dusty shroud to its stellar winds and mass loss. Fast forward to 2010, and observations using the Bernard-Lyot telescope at Pic du Midi Observatory confirmed the presence of a weak magnetic field at Betelgeuse's surface. This discovery hinted at the colossal convective motions within supergiant stars, sparking a miniature dynamo effect. Betelgeuse's journey through space is a cosmic puzzle, with its kinematics posing more questions than answers. Class M supergiants like Betelgeuse, born with an initial mass of around 20 times that of our Sun, typically clock in at around 10 million years old. But here's where things get intriguing. Tracing Betelgeuse's path backward in time places it in an improbable location far from any known star-forming regions. It's as if it took a detour through uncharted cosmic territory. What's more, Betelgeuse's trajectory doesn't seem to align with known stellar hotspots like the 25 Ori subassociation or the Orion Nebula cluster, despite their relative proximity. This begs the question, has Betelgeuse always followed its current path or did it veer off course at some point? Some astronomers speculate that a nearby stellar explosion might have nudged it onto its present trajectory. A revelation from the Herschel Space Observatory in 2013 added another layer to the mystery. Betelgeuse's mighty stellar winds are colliding with the interstellar medium, creating cosmic shock waves in their wake. But where did Betelgeuse come from in the first place? The prevailing theory suggests it's a runaway star from the Orion OB1 association, once part of a high-mass multiple system within Ori OB1A. Born roughly 10 to 12 million years ago, Betelgeuse's journey has been anything but ordinary, fueled by its mass and bulk. However, an intriguing proposition emerged in 2015, suggesting that Betelgeuse might belong to the newly unearthed Taurus OB association, adding another twist to its stellar saga. In 1998, radio telescope images unveiled the complex nature of Betelgeuse's atmosphere, revealing a complex interplay of gases with temperatures hovering around 3,450 Kelvin. Surprisingly, this gas was cooler than the surrounding region, challenging astronomers' preconceptions about red supergiant atmospheres. Instead of a uniform expansion driven by high-temperature gases near the surface, Betelgeuse's atmosphere showcased colossal convection cells, propelling gas outward from the star's surface into its surroundings. This discovery reshaped our understanding of stellar atmospheres, highlighting the dynamic nature of these cosmic giants. And that's not all. In 2009, a bright plume, possibly laden with carbon and nitrogen, was spotted extending from Betelgeuse's southwestern direction, hinting at intricate chemical processes unfolding within its fiery depths. But Betelgeuse's mysteries extend beyond its atmosphere, delving deep into its chromosphere and the shroud of dust enveloping it. Thanks to the faint object camera aboard the Hubble Space Telescope, astronomers caught a glimpse of Betelgeuse's chromosphere in ultraviolet light. What they found was fascinating: a bright patch in the southwest quadrant of the star's disk, hinting at dynamic activity within. Back in 1996, the chromosphere's average radius was estimated to be about 2.2 times the size of the optical disk, roughly 10 astronomical units, AU. Its temperature hovered around 5,500 Kelvin, revealing a region of intense energy and activity. However, further observations in 2004 using Hubble's STI spectrometer uncovered warm chromospheric plasma extending up to 1 arcsecond away from the star, potentially reaching a staggering $200 in size. At a distance of 197 parsecs, this revelation showcased the struggle between hot plasma and cooler gases within Betelgeuse's gaseous envelope, alongside the dust particles swirling in its circumstellar dust shells. But Betelgeuse's cosmic cloak doesn't end there. The first hints of a dust shell surrounding the star emerged in 1977 when astronomers noticed excess radiation emitted from positions beyond 12 stellar radii. This radiation, typical of mature stars, suggested the presence of a dusty veil surrounding Betelgeuse. Subsequent studies using heterodyne interferometry confirmed this, pinpointing the dust shell's inner radius at around 100 to 200 Australian dollars or 0.5 to 1.0 arcseconds. Yet the story doesn't stop at Betelgeuse's dusty attire. Studies conducted in the 1990s revealed a dynamic dust environment, with the inner radius of the dust shell fluctuating over time. Betelgeuse isn't one to stick to a routine. It undergoes sporadic bursts of dust production followed by periods of calm. This decades-long cycle adds another layer of complexity to Betelgeuse's stellar narrative, highlighting the ever-changing nature of these cosmic giants. In 1997, astronomers witnessed significant shifts in the dust shell's morphology within a single year, hinting at asymmetric illumination from the star's hotspots. While earlier reports suggested the presence of a colossal asymmetric dust shell extending a parsec away from the star, recent studies haven't quite corroborated these findings. However, another study from 1984 hinted at the presence of 3 distinct dust shells stretching over 4 light-years from one side of Betelgeuse, suggesting a continuous shedding of outer layers as the star evolves. Despite these discrepancies, astronomers continue to probe Betelgeuse's dusty realm. Preliminary estimates suggest that 2 outer carbon monoxide (CO) shells envelop the star, their exact sizes remaining elusive. One shell appears to extend from roughly 1.5 to 4.0 arcseconds, while the other reaches a staggering 7.0 arcseconds. To put this into perspective, if we assume Betelgeuse's radius to be akin to Jupiter's orbit at $5.50, the inner shell would span approximately 50 to 150 stellar radii, that's about 300 to 800 astronomical units, AU. As for the outer shell, it extends even further, reaching up to 250 stellar radii or roughly 1,400 Australian dollars. To grasp the enormity of this outer shell, consider this. The Sun's heliopause, marking the boundary of our solar system, sits at around 100 Australian dollars. This means that the outer shell surrounding Betelgeuse dwarfs our entire solar system, stretching almost 14 times its size. Among the many mysteries surrounding Betelgeuse, one that has grabbed the attention of astronomers and space enthusiasts alike is the one that happened in 2019. In late 2019, astronomers began to notice something odd. Betelgeuse was dimming. This phenomenon was particularly intriguing because, despite stars commonly exhibiting fluctuations in brightness, the magnitude and duration of Betelgeuse's dimming were significantly more pronounced than what had been previously observed in a star of its type. The enigma of the dimming, Betelgeuse's luminous fluctuations have captivated astronomers for centuries, dating back to observations by Sir John Herschel in the 19th century. In his seminal work Outlines of Astronomy, Herschel documented significant changes in Betelgeuse's brightness between 1836 and 1840. During this period, Betelgeuse even outshone its neighbor Rigel on multiple occasions, marking dramatic peaks in its variability. A brief period of calm followed, only to be interrupted by another cycle of variability noted by Herschel in 1849, reaching its zenith in 1852. Subsequent observations by astronomers revealed a pattern of irregular maxima and minima, with particularly high peaks occurring at intervals of years. However, from 1957 to 1967, Betelgeuse's brightness exhibited only minor fluctuations. Records from the American Association of Variable Star Observers, AAVSO, shed further light on Betelgeuse's luminous struggle, showing a maximum brightness of 0.2 in 1933 and 1942, contrasted with a minimum of 1.2 observed in 1927 and 1941. This variability in brightness sheds light on Betelgeuse's historical designation as alpha in Johann Bayer's Uranometria in 1603. Despite its red hue, Betelgeuse's luminous surges likely rivaled the typically brighter Rigel, earning it a prominent place in Bayer's celestial catalogue, even from Arctic latitudes where Betelgeuse's fiery glow and higher position in the sky surpassed Rigel's. It garnered local recognition, known among the Inuit as Wak, meaning large star. In 1920, astronomers Albert A. Michelson and Francis Pease, with assistance from John August Anderson, embarked on a groundbreaking mission at the Mount Wilson Observatory. Using a 6M interferometer mounted on the observatory's 2.5M telescope, they aimed to measure Betelgeuse's angular diameter. Their efforts yielded an angular diameter of 0.047, translating to a diameter of approximately 2.58 astronomical units based on a parallax value of 0.018. However, uncertainties lingered due to limb darkening and measurement errors, casting doubt on the accuracy of their findings. The 1950s and 1960s marked a turning point in our understanding of stellar convection theory, thanks to 2 key developments. Firstly, the Stratoscope project soared to new heights, quite literally, as balloon-borne telescopes ascended above Earth's atmospheric turbulence. These pioneering missions yielded stunning images of solar granules and sunspots, providing concrete evidence of convection in the solar atmosphere. Concurrently, the publication of Structure and Evolution of the Stars in 1958, authored by Martin Schwarzschild and Richard Harm, sparked a revolution in stellar modeling. Their work laid the groundwork for applying computer technologies to create more accurate stellar models, propelling our understanding of celestial phenomena forward. The 1970s brought in a new era of astronomical imaging technology, spearheaded by Antoine Labière's groundbreaking invention of speckle interferometry. This innovative technique revolutionized ground-based telescope resolution, overcoming the blurring effects of atmospheric turbulence to provide sharper images of celestial objects. With these advancements, astronomers turned their gaze towards Betelgeuse, employing infrared telescopes at mountain peaks like Mount Wilson, Mount Locke, and Mauna Kea in Hawaii. Peering through the veil of interstellar dust, they uncovered intricate circumstellar shells surrounding the supergiant, hinting at the presence of colossal gas bubbles fueled by convection. However, it wasn't until the late 1980s and early 1990s that a breakthrough occurred in visible light and infrared imaging of Betelgeuse. Aperture masking interferometry, pioneered by J. E. Baldwin and colleagues at the Cavendish Astrophysics Group, emerged as a game-changer. This innovative technique utilized a small mask with multiple holes in the telescope pupil plane, effectively transforming the aperture into an improvised interferometric array. The result? Unprecedented precision in measuring Betelgeuse's properties, coupled with the revelation of bright spots dotting its photosphere. These groundbreaking observations, captured by ground-based interferometers and later refined by instruments like the COAST telescope, unveiled Betelgeuse's stellar surface in unprecedented detail. The emergence of bright patches or hot spots on Betelgeuse's photosphere lent credence to Schwarzschild's decades-old theory of massive convection cells dominating the star's surface. These findings represented a significant milestone in our quest to decipher the mysteries of stellar convection, shedding light on the dynamic processes shaping the cosmos. In 1995, a pivotal moment in stellar observation occurred when the Hubble Space Telescope's faint object camera captured an ultraviolet image of Betelgeuse with unrivaled resolution. This marked the first conventional telescope image, or direct image as termed by NASA, revealing the star's disk in unprecedented detail. Unlike ground-based interferometers, space telescopes like Hubble can penetrate Earth's atmosphere to capture images in ultraviolet wavelengths. This groundbreaking image unveiled a bright patch in Betelgeuse's southwestern quadrant, indicating a region significantly hotter than its surface. Subsequent ultraviolet spectra from the Goddard High-Resolution Spectrograph hinted at the presence of a hot spot near one of Betelgeuse's rotational poles, suggesting an inclination of approximately 20 degrees to Earth's direction and a position angle from celestial north of about 55 degrees. Betelgeuse's unexpected behavior didn't stop there. In late 2019 and early 2020, astronomers were puzzled by the dramatic dimming of the star, the most significant observed in over a century. At its faintest, Betelgeuse even appeared dimmer than Bellatrix, Orion's third brightest star. This event, known as the Great Dimming, sent shockwaves through the astronomical community, prompting intense scrutiny of the star's enigmatic behavior. By August 2020, extensive studies, particularly utilizing ultraviolet observations from the Hubble Space Telescope, offered insights into the mysterious dimming. Astronomers proposed that a colossal ejection of superheated material had occurred, forming a dense dust cloud that partially obscured Betelgeuse's surface. Hubble's observations in September, October, and November provided tantalizing glimpses of dense, heated material traversing the star's atmosphere. This phenomenon culminated in a more pronounced dimming, observed by several telescopes in December and the following months of 2020. As Betelgeuse's dimming saga unfolded, astronomers and enthusiasts alike watched with bated breath. By January 2020, the star had dimmed significantly, its brightness dropping from a magnitude of 0.5 to 1.5, a factor of approximately 2.5. In February, reports from the Astronomer's Telegram confirmed Betelgeuse's record minimum brightness of plus 1.614, marking it as the least luminous and coolest in the 25 years of their studies. This unprecedented dimming caught the attention of the astronomical community and the public alike, with Astronomy magazine dubbing it a bizarre dimming. Speculation ran wild, with popular discourse entertaining the possibility of an imminent supernova. Although astronomers were quick to remind everyone that such an event was not expected for at least the next 100,000 years, the dimming event continued to fuel curiosity and excitement.